Hi, I'm John Zamit from Malta. I was conferred a BSc honorary degree in computer engineering back in 2017 and a master's degree in telecommunications in 2019. This paper aims at designing an efficient distribution strategy to support next generation live video content. So first I talk about my motivation and aim. The second section presents insights of the proposed video delivery system. Properties of the proposed architecture are then presented. Lastly, I shall summarize simulation results and analyze why the proposed system scales favorably. Some trends from the Cisco Virtual Networking Index, which depict the increase in demands. Next generation networks are primarily driven by demand, as is the case for any industry that has large OPEX and CAPEX. Globally, video traffic will be 82% of all IP traffic by 2022, up from 75% in 2017. Traffic from wireless devices will account for 71% of total IP traffic by 2022. Conveying cutting-edge media services over current generation cellular networks becomes unrealistic, and so my work attempts to formulate a network-assisted scheme designed to mitigate load from cellular networks. Standard ways of increasing the throughput include acquiring more spectrum. This is of course expensive and is limited to a factor of 2 to 5 improvement. Improving the physical layer is also an option, but the single link performance is still limited to backhaul capacity. With regards to heterogeneous networks, femtosiles are promising but expensive, and we're still limited by the backhaul capacity. So it becomes evident that the primary choking point in current generation LTE networks is at the backhaul. So a new network distribution paradigm which optimizes the usage of available resources is needed. Device-to-device communications can provide a throughput increase that is linear with user density. Nowadays, a few popular files create a large percentage of the video traffic. So is there a way we can exploit video popularity whilst retaining the on-demand capability? Yes, we can use storage or caching that is close to the requesting user. We can exploit the large storage available on modern smartphones, most of which is commonly underutilized. Exploiting the redundancy of video requests in cellular networks is not new. Current research primarily focuses on multicast and tree-based architectures, peer-to-peer distribution, and overlay networks. Multicast and tree-based architectures are totally different from conventional unicast streaming. IP multicast is a promising technology that can handle multiple users on a large scale. Many researchers have been investigating this area until the last decade. Some researchers have built centralized tree-based repair graphs, however these suffer from a high control overhead and are susceptible to node failure. There has been a strong case for peer-to-peer distribution as a low-cost CDN for many years. However, there's complexity in allocating the outbound bandwidth of peers to supply different views, and there's undesirable interruptions due to peer churn. Overlay networks build the foundation of independent virtual networks on top of actual physical network infrastructure. The drawback of this approach is that when the number of users in the connected overlay becomes large, the cost of maintaining each bridge becomes expensive. In reality, however, the bottleneck in cellular mobile networks is caused by the strenuous traversal of the core infrastructure. My solution is base station assisted direct communication between closely located UEs without data routing via the radio and core network. The base station in the radio access network has brief video buffers with caching maps. A mode selection strategy is proposed at the base station to decide whether the requester should obtain dedicated resources either via the traditional CDN or reuse existing resources via the helpers. My design is built on top of the reference LTE advanced design. The proposal exploits the resources available at helper users which cooperate with the base station to provide resources requested by the requester user. Users only store a subset of recently accessed content because playback progresses of the nodes are semi-synchronized in live video content. Buffer maps are maintained at the base station, mirroring this availability of cache segments at each node. In conventional cellular infrastructure networks with unicast video distribution, the segments must traverse via the radio access network via the base station, as well as core network resources through the packet switch domain and back, before reaching the user device. This is distinctly impractical for transmission of multi-view video, whereby huge amounts of data need to pass over the bandwidth constrained channels. My solution is to maximize the offloading probability from the helpers. We assume that each user samples one file from a given populated distribution. File n is chosen with probability Pn, and we let Pk be the probability that the choice of user k is available locally. Having such a system in place offers the best of both worlds in that we have centralized mode selection operation whilst having distributed caching peers. Other advantages include that the system's intelligence is supported at a central point of control, which leads to better efficiency for scheduling. We have no long search for who has the segment I want, as is the case in overlay networks, and operators tend to accept the base station controlled device-to-device more easily. Such an approach also incentivizes users, network operators, and content providers alike. The proposed base station cache map solution is built on top of the reference design of 3GPP Release 12 from a data plane perspective. I also implemented server and client applications, both of which are modeled on HTTP-based media delivery. This works by breaking the data stream into a sequence of media segment files, and it allows the receiver to proactively act on the overall stream in chunks, instead of waiting for the entire data to arrive. My architecture also includes evolved packet core burst services, namely the traffic flow filter and the mode selector. When the packet traverses the traffic flow filter, the source address and the destination address are surged. It queries the LTE binder to decide whether the packet must traverse over the R interface or the LTE packet gateway, and GTP encapsulation is also performed. When a packet traverses the mode selector, a mode selection algorithm is tasked with choosing the right mode, CDN or D2D. The mode selector also ensures that the buffer map contents are updated continuously with respect to the buffering capabilities on the client device. A simple algorithm is employed at the mode selector for when a video segment request from the requester traverses it. It is shown here. So, for every incoming segment request n, we store this video segment n-1 at buffer map and we schedule its deletion accordingly. The reason that we store n-1 is that an arrival of a video segment request n indicates that the previous segment has been received in its entirety. We then check if the current video segment request n exists in the buffer map, and if it does, we notify the sender of the buffer map match and we drop the video segment request in. This caching scheme is fully decentralized in that only the metadata is stored in the buffer map on the base station. Buffer map contents include the requester address, requester port, segment identifier, view identifier, and the timestamp identifying when the request was sent. Such metadata is obtained from the header data of the video segment request message. Here is some sample first in first out buffer map content, which includes the client address, the client port, the segment identifier, the view identifier, and the video timestamp. A testbed simulation for the proof of concept was also developed using Omnet++, an open source discrete event simulation package. It enables modularization of complex systems by assembling several elementary modules together. These modules are actually active components, and their behavior is implemented in separate C++ implementation files. Messages can be sent either via connections that span modules or directly to other modules. The data plane is modeled using the SIMU LTE framework, which serves as an extension to the INET framework. SIMU LTE models the data plane of the LTE radio access network and evolved packet core, whilst INET models the internet stack and many other protocols and components. The single cell LTE network model consists of an eNode B serving a variable number of mobile devices. This is the internal structure of the SIMU LTE eNode B, where it includes the mode selector and traffic flow filter modules described earlier. On the other hand, this is the internal structure of the UE. Both the eNode B and the UE were implemented as compound modules with their respective submodules and their corresponding SIMU LTE network interface card. UDP applications are implemented as vectors of N modules, thus enabling multiple video views per UE. Each UDP application represents one end of a connection, with the other end located within the video server. My analysis includes a number of scenarios, each representing different video environments. The first three scenarios assess the performance of the system with a varying number of users and a fixed number of views, whilst the second set factor in different number of views for a fixed set of users. Both scenarios go up to 10 users and up to 7 views respectively. Each scenario was repeated under two parameter studies, one which changes the overall video bitrate, where I've included bitrates of 1, 1.6 and 2 megabits per second. These are typical bitrates for 1080p HD video content. And I've also changed the buffer size capabilities of the user devices, where I included buffer sizes of 2 seconds, 5 seconds and 19 seconds. All simulations model a two-scale system deployed at the University of Malta MCDA campus, with an LTE base station lodged atop the central library building. This clip demonstrates the third scenario, where we have 10 users over a period of 200 seconds. From my results, a considerable improvement is noted with the proposed system in place. Results demonstrate an average load savings of 30%, with savings of up to 59% in certain scenarios. Exceptionally better performance was noted as the load in terms of views and users is increased. There is higher potential for load savings in the network. As a result, more users work independently and collectively contribute to the overall system performance. The added computational complexity and signaling overhead this system introduces has no significant influence on the statistical data recorded for the delay and the jitter. Here we have the third scenario where we have 10 users, all of which are streaming to views. The chart on our left shows the video bitrate study, where we have the y-axis indicating the video bitrate in terms of megabits per second, and the x-axis showing the number of packets paused. The chart on our right shows the client buffer size capability study. The y-axis shows the client buffer size in terms of seconds, and the x-axis shows the number of packets paused. Here we have the sixth scenario where we have 2 users, all of which are streaming 7 views. Higher buffer size capabilities at the UE and higher video bit rates result in higher packet availability and hence better chance for load mitigation in the network. The key design in my approach decouples the cache and the cache availability information as much as possible. As seen from the results, such an approach can reduce load on the LTE backbone by several orders of magnitude. The performance obviously depends on the reuse of video content. For example, when the buffer size is reduced, less segments are stored at the UEs. Furthermore, with lower video bit rates, the client's playout buffer remains underutilized. Thus, when considering deploying the proposed system, it is important to determine the buffer capabilities of the UEs with respect to the video bit rate. The proposed method not only guarantees an overall improvement in per-user view data throughput, but also achieves this with little to no effect on the delay parameters.